Hello everyone, I am Yannick Balquin. I will present you this webinar entitled Specific Metallurgical Issues in Additive Manufacturing of Toolings. I will focus on fusion additive manufacturing techniques. And to present myself, I'm Yannick Balquin. So I work in the Laboratoire Génie de Production in France, in Tarbes, small city, approximately 150 kilometers from Bayonne. I am working with Morgan Mokhtari and Joel Alexis. We are the metallurgist team of the lab. There is 30 people in this lab dealing with material and mechanical science. And we have 3 metallurgists. So, first, I will propose you a short reminding of specific microstructural features in fusion additive manufacturing, and we will focus, second point, on LMDW processing of 15 CRMO V6 alloy, and we will then go on the W360 processing. It's a tool steel alloy. I will end with a brief summary and prospects. First, the reminding, in additive manufacturing, in fusion additive manufacturing, is as in welding process. We will experience, in the case of simple deposit, for example, we will have a moving heat source that allows melting of the material and creation of a melt pool. In case of additive manufacturing, is filling by filler wire, and then that you moving this heat source and filling, you obtain a single deposit. It's quite simple in this case, but with a cross section of this melt pool, you can observe that we have a complex shape of this melt pool section, but also we have a heat affected zone under, and it became less simple when considering that we have this moving melt pool, the filler wire or powder bed. We have a remelting front that is first not important at the first side, but we have a solidification front, and this solidification front is hard to understand and in this governing microstructural formation, but also not only on the solidification front, but also in the heat affected zone. So how does the metal solidifies in such welding or additive manufacturing process? First, we have thermal gradients within the liquid melt pool. Okay. In the second, we have melt pool dynamics, so movements of liquids in this melt pool induced by thermal gradient, but also on mahogany induced convection, and sometimes in Lorentz force in case of arc additive manufacturing. So we have melt pool which metal is moving with thermal gradients, and also we have different solidification rates considering this bulbous melt pool and this trailing edge of this melt pool. So it's all governing microstructure of the produced part. So we need to understand bits of metallurgy and solidification theory to understand the specificities of additive manufacturing of metals using fusion process. So when you have a liquid and solid phase of metallic material in equilibrium or near equilibrium, we can observe sometimes protuberance on this interface, in excess of solid. We have to question that if this protuberance is stable. If we are in the stable process, it will remelt. Or if we have a thermal gradient or disequilibrium between liquid and solid, like in welding and additive manufacturing, we will have a growth of this protuberance, and we will have a solidification that is going through. Is it a cellular dendritic growth? The cellular growth is characterized by columnar solids with a liquid film between these columns, and this liquid film is getting thinner and thinner as solidification front goes on, and as cooling of this semi-solid is increasing. So we have another configuration with dendritic growth. The main difference is that we have secondary branching on this columnar solidification, and that they are characterized by this lambda 2. It's the secondary arm dendritic spacing. So what kind of microstructure can we obtain in additive manufacturing? In conventional additive manufacturing, we have to understand solidification structure. So the liquid-solid interface is governed by temperature gradient and growth rate. So using a GR diagram, you can understand that we can have planar growth. It's a possible case, but cellular and dendritic growth, and dendritic growth is mainly helped by low temperature gradient, conversely to cellular or planar solidification. In additive manufacturing, we have to understand that melt pool is very small compared to the part size. So the part acts as a heat sink, okay, and we can have very great temperature gradients compared to casting process, for example. So we have high cooling rate, high temperature gradient, and high grow rate. So we can position different processes like wire arc additive manufacturing, producing for given material, for example, a columnar dendritic structure, and for LPBF, we can observe more than cellular microstructure with a high growth rate and high temperature gradient. So we distinguished cellular and dendritic growth in additive manufacturing of parts. It's to be related also to composition of alloy. And for some alloys, we do not have any dendritic structure, for example. To understand also micro and macro structure in fusion additive manufacturing, we have to notice that solid and liquid phase normally have the same mean composition, and the crystal growth is using the solid phase, a seed crystal. So we have an epitaxial growth and a favorite growth in 1-0-0 directions. So we have competition between grains growing at the liquid solid interface, and the well-oriented grains win the game and will end the solidification process. The solid base metal is also, in most of the case, a previous deposit. When you build a part, you have a previous deposit, so it could be quite hot. For example, in arc additive manufacturing, when you are building a small part without interlayer delay, or in case also of warm parts, we have very big parts, and between two layers, we have sometimes a few minutes, and the cooling delay is very important. So we could have in the same part, in a single part, a strong heterogeneous microstructure. A third point is to consider that we have multiple fusions and cumulative heat treatment due to layer stacking. When we take an example, single deposit in construction progress, the first deposit, the first layer is melted, evidently, and is now cooled. But when you put the second layer on the first and the third layer on the second, you can observe induced heat treatments in the previous layer. Sometimes it's only remelting, sometimes it's remelting and heat treatment. And then you go out to the last of these layers, and the 10th layers also produce the heat treatments in the first layer. But also you have to note that the whole part is getting hot. We have a progressive heating of the part, and it's named thermal reloading. So we have a very complex solidification microstructure, but also this microstructure are modified by cumulative heat treatments. The last problem we have, the last issue is cracking. We have to understand that in dendritic solidification, we are partitioning alloying elements at liquid-solid interface. Some elements are getting in the liquid phase, and some are in the solid phase. So we have segregations. And then, in the point of view mechanics, we have a shrinkage of this material during cooling, and we have differential shrinkage, and we have a semi-solid material. So we have liquid phases that have no mechanical properties submitted to tensions, and so we can observe hot crackings. An explanation is that in the trailing edge of this molten pool, we have dendrites that are growing, and we have liquid phases between dendrites and trapped liquid domains that cannot withstand tension solicitation without opening, without cracking. A second point is that we use in most tooling sectors, we are using steels, and the hardening of the steel is based on martensite formation, most of the case. So we have a sudden hardening during cooling of this material under martensite start temperature. And we also experience high levels of residual stress during formation between strong thermal gradients. So we can observe sometimes cold cracking, so different type of cracking, but same results, poor material health. In summary, to get a brief summary of this aspect in additive manufacturing, we can think that we work with a moving melt pool, and remelting and heat affected zones in this material. We have an epitaxial growth in grain, generating a grain structure from the substrate to the top of the part, and we have a strong anisotropy in these materials. And we have both high cooling rates and high growth rates, implying thin dendritics or even thinner cellular grain growth. We have late heat treatments in these previous layers. So the top, the last layer have nothing except composition. Sometimes you have nothing to deal with the other layer of the part. So we have a very strong microstructural gradients, and as in welding, we can expect that if we use high performance alloys in additive manufacturing techniques, we can expect cold and hot cracking. So on the first example, I will deal with LMD proceeded 15 CR-6. It's a very useful alloy in aviation and aerospace. It's 1.5% of chromium and 1% of molybdenum. This alloy have fair mechanical properties and is also sensitive to heat treatments, so we can modify its properties. Quite interesting. And its last advantage is that it's employed in aircraft subframe that are welded and is available in filler wires. So STR built a deposit on the substrate. This deposit is several millimeters thick and 80 millimeters high, so we can perform investigation, mechanical and microstructural investigation. The building process was the following: the layers using a scanning strategy, okay, and the subsequent layers was the same strategy but crossed angled. So analyzing microstructure, this part, this prototype, we observe that we have an homogeneous microstructure consisting in mainly martensite, tempered martensite or benite, but hard to distinguish. But we have good mechanical properties, and we have no hardness gradient between just above the base plate and the top of the building. We have no chemical gradients. We have no significant difference in material composition between the first centimeter and the top end. So we have only in the vicinity of the base plate, we have very odd microstructural features. So we've built a ferritic alloy on austenitic one, austenitic stainless steel. So we have some unmixing features between these two alloys. We have with complex shapes, with lens shaped, with islands, okay, and we have also gradient of composition of material structure. So when you take bits of this microstructure, we can achieve mechanical hardness, and we can observe that the deposit has the standard hardness of 315 hardness, Vickers hardness. So here we observe the transition between the very soft austenitic stainless steel and an area where we have iron diluted 316 and the quite pure 15 CRMOV6 deposit. So we have islands of these alloys in the iron diluted stainless steel matrix. This is a gradient of composition. We can also understand mechanical properties of the deposit, just the deposit. Performing tensile test, we can observe that we have good mechanical properties within the range that the roped material can achieve. The important by hardness, we've determined that we have homogeneous microstructure and mechanical properties by hardness, and then we can expect that we will have an homogeneous behavior. But looking at the sample, with which is the tensile test sample, which is etched, we have a white band on it, and we have to understand what this feature can modify mechanical properties of the material. So by digital image correlation, we've performed analysis, and we have observed that this specific area is locating deformation. So the mechanical properties measured on this tensile stress, tensile strain diagram is not the real mechanical properties, because we have a microstructural gradient, slight modification in this, and we observe a strain localization in this kind of heat-affected zone. It's due to a pause during the building of the wall and different thermomechanical history in this area precisely. So now we get back to a tool steel W360 preceded by LPBF for a very different application. So this alloy is W360 developed by Boller, has high content, quite high content of chromium and niobium. It's given to have a relatively high hardness, okay, high impact toughness, and in rocked condition it has homogeneous microstructure. The powder provided by Boller is given for the same hardness and the quite comparable impact toughness on conventional V-notched sample, and produced sample were analyzed first in terms of material parts. Using cross-section, we can observe different dots, different pores, different micro cracks maybe. So we used to investigate material earth using image analysis, and we've observed that the average surface density was above 99.8%, and we have a very small defects in this image with a maximum defect diameter just under 18 microns. So we have a very good material as at the beginning, considering an LPBF process. On the skin of the produced sample, on the side skin, we can observe different pores, okay, relatively big pores just under the skin of the sample, and it's due to a contouring effect. But the skin of this part has to be machined, so it's not very a very hard defect that we observe. Another defect that we observe this time on the top of the build is some micro cracks. Okay, you have here different photographs with an etched sample that you can observe the shape of these cracks. But this surface will be subsequently machined, so it's not very important issues in this material. So concerning macrostructure, we have measurements of melt shape on the last layer produced. We have nail head shape with approximately 100 microns wide and 200 microns height. It's only visible in the upskin, okay, and we can observe that the chemical etching is very different between this last layer and the rest of the material. In these areas, we can observe also at the lower scale a microstructure, a cellular microstructure composed of these thin cells, okay, separated by a very, very thin intercellular phase. And within this cell, we can observe some kinds of martensitic features like lath or kinds of needles. So we can expect that we have different cooling rates because we have different cell size between the skin of the sample and the core. We have very, very thin cells, so we did not completely understand what was the real material composition in this cell and out of these cells. We do not have the chemical gradient. It's to be investigated, but we have an initial microstructure quite interesting. The hardness of this material is quite homogeneous. We have very slight anisotropy between building planes and building duration. But on the upper skin we've tested, we have very, very high hardness. We have micro cracks, you can see here, but we have very high hardness above 800 HV0.2. So we have low anisotropy, we have an upskin defect that will be removed by subsequent machining. And the mean hardness we obtain is within the range of the supplier that achieved. About tensile properties, it's very interesting to see also that we have a difference between vertically built samples and horizontal built samples. The horizontal built samples have lower mechanical properties, same behavior, but the strain hardening is very, very low. So we can observe that on vertically built sample, we have no upper skin effect and no down skin effect also. Here, when we polished the sample, we did not remove all the features, all the microstructural features in the skin, in the top skin and the bottom skin. So it can explain the difference between of behavior between gray samples that are vertically built and orange samples that are horizontally built. These values are very, very are quite low compared to the border, but it's after heat treatment, it's expected to be enhanced. Okay, and we've explained the difference, the anisotropy respect regard to building direction. We've also performed sharp impact tests. We are just under 10 joules per square centimeters on V-notch samples. Border is giving a higher value, but we can observe on fracture surface quite a brittle behavior. Okay, and we can observe features that are in terms of their size in the same size of the melt pool we've observed. So we can expect a different behavior, different fracture behavior between these different melt pools. So we have a fair material, we have a good material earth and the potential of hardening after the suitable heat treatment. So to understand the effect of the heat treatment, we have to study this mechanical metallurgical transformation, thanks to dilatometry. The principle of dilatometry, in few words, you have a sample and you measure variation of its length during heating and cooling and also holding steps. We can achieve, thanks to induction heating, high cooling rates and high heating rates also, because we can cool quite fast this sample with a different apparatus that is not shown in the scale. So we work on inert atmosphere, and we can, thanks to push rod, measure the behavior of this material. The sample size is 10 millimeters long and 3 to 6 millimeters in diameter. Its application of dilatometry is to understand cooling transformation, so to build CCT diagrams or CHT diagrams for heating, and TTT diagrams for isothermal transformations. We can also, thanks to this system, determine the curing temperature of steels. So, heating, post-indentation, and cooling profile we can achieve with this apparatus. We choose to heat at 15 degrees per minute. We have holding and stigmatization at 1050 degrees for 30 minutes, and we cool with different cooling rates at room temperature. So, using this time the length variation versus time, we can observe that in heating process, we can observe a small anomaly in dilatation, thermal expansion of these samples. It's it could be the austenitization. And at the cooling, we also observe anomalies on the cooling of the material. We have to notice that we have high levels of deformation of thermal dilatation using alumina push rods, different for quartz push rods. So with the derivative of this information, we can better achieve understanding of different length variation anomalies. So we can propose induced metallurgical transformation in this temperature range. So we use derivative data for understanding these transformations. So using different cooling rates and comparing to the conventional CCT diagram of this alloy, we can observe that we have very few modification on Martensite transformation. The Martensite start is the same as the work material. The benitic transformation is very, very comparable to the work material, but on paralytic transformation here we have modification of the paralytic domain, paralytic transformation domain, with a low level of cooling rates. So we can be confirmed by the fact that we have a hardness quite low for the maximum, the minimum cooling rate we achieved, and is not comparable to the work material. So do we have an effect of the slight composition modification between the powder and the work material on vanadium, for example, or it is related to initial microstructure of the sample? So to give a brief summary and more prospects on these two studies, I would like to present a brief summary on 15 CR V6 results obtained by directed energy deposition by wire, who have good mechanical properties to build some kind of geometric assessment tooling. We have an original mixing of austenitic base plate and ferritic build part. Okay, it's an original feature, but we have good mechanical properties in as-built condition. For W360 in LPBF produced process, it was expected to use this material as injection molding inserts, but in such kind of application, we need very good material health, but all the features that we observe, porosity under the skin of the material, small cracks in the top surface, will be removed by machining, subsequent machining. We have promising as good as-built properties, but we are far under the specification of ball. By a conventional heat treatment, we can achieve the original properties, but it could be interesting to understand how we can propose original heat treatment. For example, we can starting disrupting this cellular microstructure, this cellular as-built microstructure, and we could use it to have a new combination of hardness and of toughness. So we have to understand austenitization and homogenization of this material. So we have to perfect study on heating of this material, teleotometric studies, for example. I would like to thank you for your attention, and I am ready to ask to respond to your your questions. Okay. Thanks. So to my answer to Josu Lopez, we did not have heat-treated materials. So we expected enhancement of mechanical properties using a conventional heat treatment, but we do not have any results on heat-treated material on Sharpie tests. On W360 compared to H11, I don't have any information on thermal conductivity of W360. We did not compared specifically we worked on H13 alloy, but by FDM process, so without fusion, with debinding and sintering process. So I don't have any comparison on LPBF produced W360 and H11. Hi, Fabio. I hope first, Mr. Martinez Alvarez, I hope I answer your question. And Miren Nancy Zidor, I will answer your question. W360 sample were produced at by Fabio Simões, I think, in Ipeleria, in Portugal. He is online, and maybe we can answer the question. Fabio, you have a question about the cellular structure and chemical composition of the cell and cell walls. We did not achieve a good characterization of this chemical gradient. So we have to use transmission electron microscopy to achieve a very good microstructural analysis at this scale. We are in sub-micron scale, so we have to use transmission electron microscopy. So it's the kind of studies the kind of problem we will investigate in the following month. Okay, the scanning electron microscope we have is not able to achieve a chemical analysis on such small scales. I would like first to thank you all for hearing me, and I will propose you to get in touch with Joel Alexis. He was part of the Additool project. He's the professor of the lab that is dealing with metallurgy, material science. And if you have any question later, you can contact us via the Additool and AFM consortium. Okay. Thanks a lot, everyone.